Okay, hopefully you heard the announcement that the meeting was being recorded, because I'm not hearing anything. So I'm curious what you've had to review to complete, okay, good, to complete the homework. All right, integration by parts, integrals of trig functions. And I was wondering about that because I got some pushback on the U sub. Okay, we did some U sub in class. I think we did an integration by parts in class. Limits and integration rules. Integration by parts. All right. Okay. So the integration by parts is going to come up some more. So I'm going to write myself a note to make sure I get you some more review on that. All right, we spend time in Calc 2. We spend time in Calc 2 doing all these trig substitution type integrations that you will probably never see again the rest of your life. So integration by parts and U sub is a lot of what you're going to see is integration by parts and the U sub. Okay, I'm wondering about the trig substitution because of some quiz issues that I was seeing. And so that makes me, so I'm also going to write that down. I understand that WebAssign can be frustrating. If you want to send me an email, I'm happy to go back and relook at it. I did get an email yesterday, but I actually teach Sunday nights. That's when my online class, that's when they do their thing. So because of that, I don't get a chance, I really didn't get a chance to look at anything. I was busy teaching. All right, so. Okay, let me go ahead and get my notes. My goal today was to go ahead and, here it goes, go ahead and do some lecturing on 13.3 and 13.4 today. You'll notice 13.3 and 13.4 have been pushed back, and I believe I got those quizzes set up for you. Now, I actually took a workshop on the using WebAssign to give exams, and it's doable. I think as students, you would find it to be a complete nightmare. I'm just being honest. The reason why is because, believe it or not, what they recommend is you only see each problem for about 10 minutes or so. And I don't think you want to be doing that. You don't have to upload your work. You only, WebAssign quizzes you have to submit work for. The only problem is if you come to me and you're like, by the way, I need you to look at this problem, then I'm going to want to see your work. Okay, so that would be the only potential issue. But no, as a rule of thumb, you don't need to do that. All right. Okay, so I'm going to go ahead and I'm going to share my screen. There we go. So let me know in the chat if you guys can see about arc length and curvature, and we can get started on this. Okay, by the way, I watched a fascinating documentary on Netflix last night. I was thinking about making it extra credit, but I don't know if everyone has access to Netflix. Then again, you might want to have Netflix parties. So maybe I'll do a poll on it, but it's called Social Dilemma. And it's interesting from a math standpoint. Actually, I think I might have you guys, I might have you, okay, if you guys want to do a Netflix party, Perla saw it, so she saw how dangerous it is. It's basically, it doesn't do math, but yeah, I'll open up a Dropbox and you guys can write me a paragraph about what you thought. All right, it's called Social Dilemma, and it's about the algorithms that are used. Social Dilemma. Here. It's probably spelled wrong. Someone spell it for me properly. Perla can spell it. Yeah, there we go. I flipped the letters around because my technology isn't working, so I'm having issues. When I get nervous and upset, my dyslexia goes overboard. All right, so yeah, so it's Social Dilemma, and it's about the algorithm that they use in order to have you addicted to social media. And there's a woman in there with blue hair. And I actually heard her speak a couple of years ago at a conference. And I wish they had brought her in more, because her work, she actually has a book out called Math, the Weapon of Mass, or no, the Weaponization of Math Destruction. But it's fascinating, and it has to deal with algorithms. And I bring that in a lot when I'm teaching the business calc class. Okay, so yeah, so Social Dilemma, I don't spell, but yeah, I'll go ahead and open it up. And between now and the end of the semester, if you want to sit and watch it, it will really kind of open your eyes about social media and what have you, and the purpose of it. And it's just really, really fascinating. Okay, so I got some comments that 13.3 was difficult, and we are going to work on that today. I did give you a review, so to speak, about this, but let's go ahead. And I think one of the biggest problems with this one is the trick. And I hate calling them that, but this is really what it is. All right, the trick for this is you're going to need to look for a square. And I'll show you what I mean. And if you look for the square, then your answers are going to fall out a little easier. Now, back in Calc 2, we did arc length. And the equation from Calc 2, which I think was on your pre-quiz, is that the basic equation for arc length, square root of dx over dt squared plus dy over dt squared dt. Okay, so back in Calc 2, you did problems that look like this. And from an integration standpoint, you'll notice that if we can get rid of that square root, our life would be a whole lot easier from integration. And that's why I said the trick for this is to look for a perfect square. So I'm going to take you sort of way back in time. All right, and let's talk about a perfect square. I know I got a bunch of tutors in the class. Feel free to go get a cup of coffee as you're rolling your eyes. All right, if I have x squared plus 4x plus 4, I can then factor that to be x plus 2 squared. Okay, if I have, let's say we have x squared plus 6x plus 9, this can also be factored to a perfect square, x plus 3 squared. And the reason why you want to look for these perfect squares is because then if you have a perfect square and a square root, if we have an integral of the square root of x plus 2 squared, right, then those are going to cancel and you end up with an integral that is rather simplistic. And I noticed someone mentioned in the, and I asked how it was going, that, 3.3 was giving them some struggle. Okay, and I think probably the reason why is you need to be on the lookout for these perfect squares. Okay, so what do we need to think about? There are two things we need to think about. One is that perfect square, and the second is the trig identity. Right? Sine squared of theta plus cosine squared of theta equals 1. All right, and so those are the two things that we're probably going to want to look for. What you will notice is you don't always have x's. And then let me write this down and then we'll move into 3D. All right, you might have something that looks like this. E to the 2t plus 4e to the t plus 4. All right, and that has a tendency to cause students a lot of problems, and we will do one of these in class. But if you think about it, you can almost, in your notes even, or in your brain, do a substitution. So this ends up being x squared plus 4x plus 4, which is then a perfect square. All right, so this, I know for a fact, this has a tendency to trip students up. So look for that, okay? All right, any questions about this, or are we ready to move into 3D? Looking at the chat. Too many people went and got coffee. Okay. All right, excellent. Okay, so, let's not, okay, let's go ahead and look at the equation of the arc length, but we're going to look at it in 3D. All right, so if you think about it, the arc length, all right, this is then going to be dx dt squared plus dy dt squared plus dz dt squared dt. Okay, that is certainly one way to look at it, but in 3D space, what have we determined? We've determined we really don't need these ugly complex equations anymore, do we? Instead, we can now work with vectors because the vector tells us any point of where it's going on. So if you think about it, where do we have this type of scenario happening? And usually this is called an S. And that is if we integrate the magnitude. All right, so that's really what we're going to be looking at, is we're going to be looking at integrating the magnitude. And this is a little bit of a simpler equation because then you also know ds dt is then strictly the magnitude, which is kind of cool. So if you think about it, right, how the arc length is changing with time, that we're measuring, that distance along that arc length is changing with time, is the same then as the magnitude of our position vector. Okay. All right, are we ready to do a problem? Yes, that is R prime. not just r. You're welcome. Okay, let's go ahead now and do a problem. Okay, so we want to find a length of the curve, and this is the type of information we're given. Okay, now by the way, Chris, to back up just for a moment, it's r prime because remember it was dx dt, dy dt, dz dt. So it's the derivative with respect to t. So if we go ahead then, yes, it's the magnitude of the velocity vector, correct. All right, so, and we're actually, hopefully we get to do 3-4 today. We will do 3-4 today. No questions asked. We're gonna do 3-4 today. And so we're actually gonna work with acceleration vectors, which I know you've been told doesn't exist, as well as velocity vectors and position vectors. Okay. All right, so let's talk about this. R prime of t, right, because we're gonna be doing what? If we want the arc length, right, we're gonna integrate it from A to B, and then it's gonna be the magnitude of the derivative dt. So we need to start off by taking the derivative of this. So this is then gonna be negative sine of t, cosine of t, and a 1 when we take the derivative. All right, now let's go ahead then and look at what happens when we do the magnitude. And that's why I said there are two kind of tricks we're going to have to do with this. All right, so here we go. All right, we're looking at this. I teach is derived. I need to put a mask on. I don't know how well you guys can hear me, but I'll give it a shot.
You don't put a mask on.
You sure?
Yeah.
Okay. All right. So looking at this, what can then happen, right? We can then square root. This is then going to be sine squared of t plus cosine squared of t plus 1. Now, that in itself would be a little ugly to integrate. All right. Can I get someone to unmute real quick? Perla, can you unmute and see if we fix the sound issue?
Did you look at the slider?
Yeah.
Can you hear me, Dr. Minky? Hello?
Oh, wrong. This is the wrong slider. Hang on.
Can you hear me?
When you slide, do you get a sound?
No. Someone unmute and talk to me. Yeah, she's unmuted and talking and nothing is coming through.
Yeah.
The only thing I can recommend, the only thing I can think of is restart the computer.
Okay. All right.
Everything is working. You're on the right projector.
All right. Okay. Well, then that's fine. I need to finish working with them, and then between classes I'll restart.
Okay. All right.
And I'll keep you posted. Thank
Okay.
you so much.
Okay. Or the volume here. Which one?
Either one works. Either one works. Okay. Yeah, it's not working. Yeah, Andrea, I understand that, but when but it's not, it doesn't seem to be working. So yeah, that's what he was just looking at. All right, so sine squared plus cosine squared is 1 plus 1, right? So that ends up being the square root of 2. Square root of 2, that's not very hard to integrate. And let's double check our limits on this. Our limits are when t goes from 0 to 2 pi. So I'm going to integrate from 0 to 2 pi square root of 2 dt. All right, so that becomes square root of 2t evaluated from 0 to 2 pi. And so our answer is then 2 pi square root of 2. All right, does that make sense? How does that work? It's much easier than it looks. It is, Hannah, as long as we look. In the next couple of problems we're going to do, we're going to look for that, that square business. I've got 3, 3, and 3, 4 all plugged in together. All right, so let's look at one of the square businesses. And then, as I said, we're going to come back and look at one of those e raised to the t. I'll just pull it out of your homework, I guess. All right, so let's go ahead, write this one down. Yeah, you want number 2 on 13.3? Not a problem. I will pull that out right now. Okay, so this one is also, right, we want to find the length of the curve. So in order to find the length of the curve, we're going to look at this type of scenario. Usually in 3D, it's called S, not L. And I'm not sure if that's your author's notation or that was the dinosaur notation. I can't remember. All right, now this one looks a little uglier. So let's see what we're going to have to do for this one. Once again, I have sines and cosines. So that's a good thing, isn't it? Because sines and cosines can go to 1. But let's see what happens when we take the derivative on this one. We're going to end up then with a 6 sine of 2t. This is then just going to be a 4. All right, and then this here is then going to be a 6 cosine of 2t. All right, so that's going to be what? This is then going to be negative 6 sine of 2t squared plus 4 squared plus 6 cosine of 2t squared. So this ends up then being 36 sine of 2t plus 36 cosine of 2t. Oh, that's squared, isn't it? Plus 16. Okay. All right, so let's go ahead. We could pull a 36 out of here. So that goes to 1, 36 plus 16. We end up with the square root of 52. Let me pause for a moment. Okay. All right, and so then we end up with the integral 0 to pi square, that doesn't look like a pi. Square root of 52 dt. So that's going to end up being square root of 52 times pi. All right, let's go ahead and do one more of these. And that was the one that you requested. All right, so let's go ahead, and this is your homework on WebAssign, and it is number 2. All right, now your answers might look a little different than mine, depending on what numbers you actually get. So these are the numbers I got. We have square root of 2 times t plus e to the t j plus e to the negative t k. All right, so once again, we want what? We want to know what the arc length is. So we're going to have to start this by taking its derivative. So let's go ahead then and do that. The derivative of this is then going to be the square root of 2. This is just going to be e to the t, and then this is going to be negative e to the negative t. All right, now let's go ahead and put that into our magnitude expression. So I'm going to have negative 2 squared plus e to the t squared plus negative e to the negative t squared. Is it making sense so far? Are we doing okay, Eric? Oh, Joseph, Joe, are we doing okay? Okay. All right. So this is then going to turn in the square root of 2 plus e to the 2t plus e to the negative 2t. Okay, this is actually a perfect square. All right, and if we look at this, right, this is a 1 here. If we take this e to the negative 2t and we take the square root of it, we would end up with an e to the negative t. All right, if we look at this one and we take the square root of it, we would end up with e to the t. If I multiply these, or if I'm multiplying these two together, I'm going to end up with the e to the t minus t, which is then going to be 1. So we can rewrite this as then the square root of e to the t plus e to the minus t quantity squared. Okay, so no plus 2. What's going to happen is, and let me show you why it's not a plus 2. All right, if I have e to the t plus e to the negative t, and I'm multiplying that by e to the t plus e to the negative t, right? What's this going to be? Well, we'll have e to the 2t, right, plus e to the t, e to the negative t, plus e to the t, e to the negative t, plus e to the negative 2t. Okay, these are going to then both be 1. So we're back where we start. E to the 2t plus 2 plus e to the negative 2t. And it's because you have a positive t and a negative t. All right, so we end up then, and this is going to run from 0 to 5, right? And then, well, I'm rewriting it this way. E to the t plus e to the negative t quantity squared dt. Those are going to go away for us. And we end up then between 0 and 5, e to the t plus e to the negative t dt. All right. The 2 got sucked into the square, for lack of a better word. In essence, it became our middle term. You had to go backwards, Chris? Do I need to go this way? All right, this business here, oops. This business here was almost sort of like a check. Number 5 is sine and cosines. And yeah, you're going to end up exactly with the same thing that we just did for number 6 is completely different. But we're going to have to do this again in for number 6. Okay. All right. I'm also, let's go ahead and look at another one in the homework that I want to make sure I expose you to. Okay, that's curvature. All right, so this is number 4 in your homework. And I'm not going to work it through for you. Just think about having a perfect square. But we're talking about the intersection between a parabolic cylinder and a surface. All right. So we have a parabolic cylinder, which is then what? It's going to be x squared equals 2y. This is the problem I got. And we're going to have a surface all right, and the surface is, I'm trying to read my handwriting, 3z equals xy. Okay, now this is going to be a curve, right? If you think about it, because what's happening is we have a parabolic cylinder. It's going to be hanging out on the z, right? And this sketch is not to scale or anything. This is then going to be what? This is then going to come through here, all right? And so in doing so, it's going to cut a piece out of it. What's confusing, I think, is, I'm sorry, I didn't mean to do that. What's confusing, I'm concerned about, is setting this up then as parametric equations. So we have x squared equals 2y, and we have the fact that 3z equals xy. Yeah, we're given a point. The point, and your point may vary. I got 2 to 4/3. All right, I'm not going to work this one through because instead I wanted to make sure that you see how to turn this into a parametric equation. All right, and here is the key. You're going to have to take one variable. In theory, it won't matter which variable you use, but you're going to have to take one variable. And I said, I'm going to let x equals t. All right, because then looking at the cylinder equation, y then is going to be t squared divided by 2. And looking here at the z equation, right, 3z equals t times t squared over 2. So z is then going to equal t cubed over 6. All right. We had to do this last time in the sense that we're given a point, 2 to 4/3, right? I know x equals t, so t is then going to be 2. So you're going to set your integral up from 0 to 2. Oh, sorry, that should be a 2. Okay. All right. That should get you through. Number 5 is a sine and cosine, so those will go away for you. All right, and so that leads us to problem number 6 in your homework, and we're going to have to get some other information to do problem number 6. All right, and so we're going to have to start talking about curvature, as well as, well, go ahead and get this written down, but we also need to talk about how to find the normal vector. All right, so let me know when you have this equation written down. Someone has turned on their, don't know why I have a random red spot. Is that my random red spot? Nope. Oh, here, eraser. Nope, someone has turned on their whiteboard. Okay. All right. So let's talk about this. Curvature is this kind of K-looking thing. And that is what? That is the prime of the tangent vector divided then by the derivative of our R vector. Or another way to look at it, and there should be a prime here, I believe. Let me double check that. That should be a prime there. Should be a derivative there. Okay, now there are some rules to determine curvature. All right, first off, the curve has to be smooth. Sort of the same as our derivative, right? And when we say smooth, that's a cross product. Those are vectors. That's a cross product. All right, it has to be smooth. And when we mean smooth, what? We're talking about no breaks, obviously. And the other thing is no corners. All right, so what does curvature do? Curvature right, tells us how quickly a curve changes direction. Okay, now these equations, hopefully you've written them down. These are when we're dealing with our parametric equations and vectors. Okay, if we have this type of scenario, here's another equation you're going to need. All right, if you have a vector equals f of x, all right, then your curvature is then going to be y vector double prime, the magnitude of that over 1 plus y prime squared raised to the 3/2. Right, and that's only for a special case. All right, so let's go ahead and find the curvature of a problem, and then we will talk about the tangent vector and the normal vector. Are we good to go? Hang on. There we go. All right, so here's our problem, and we want to find the curvature. Why we don't use T prime? It's not defined that way. Okay, it's R prime. Well, you can use T. You can use T prime over R prime. Yeah, but it's not a double prime. It just depends on what you have and what you're working with, Joe. All right, I'm going to go ahead and use this one, using it from a vector standpoint. Yeah, you can use T prime over R prime. That's fine. I'm going to go ahead though, and I'm going to look at this one from a vector standpoint, just to give you a couple of different ways to look at these problems. There's usually multiple ways to approach the problem. All right, so if we just want, we're given this and we just want curvature. Now, if we want that tangential vector or we want the normal vector, we're going to have to use, we're going to have to do some things a little differently. All right, but this is then r prime of t crossed r double prime of t, all divided by, and we want the magnitude of that, okay? And then that's then going to be divided by r prime of t cubed. Okay. So I would like to do one using this formulation. I know that in the homework, they have you find, as I said, the tangential vector and the normal vector, and then use those two to find the curvature, and we will certainly look at one of those as well. All right. Okay, so let's start off by figuring out what our r prime is. So our r prime of t, well, let's see, that's going to be 3i plus 4 cosine tj minus 4 sine tk. All right, hopefully my signs are correct on that. Let's now look at our double prime of t, because we're going to have to cross those two together. Well, the derivative of the 3 is just going to be a 0. So then this is then going to become negative 4 sine tj minus 4 cosine tk. All right, so let's go ahead then and look at this cross product. So we're going to have 3, 0, 4 cosine t, negative 4 sine t, and I think you can see what's going to happen with this. Negative 4 sine t, and this is then negative 4 cosine t. All right, let's look at each of our components. Our I component is then going to be what? It's going to be negative 16, right? Cosine squared of t, right? And then we're going to have minus a negative 16 sine squared of t. Oh, no, that's going to be the first one's negative. The second one is going to end up being positive, isn't it? All right, so minus 61. I don't understand. So this equals negative 16. All right, let's look then at our j component. Okay, so our j component is then going to be negative 12 cosine of t minus 0. So that's going to become negative 12 cosine of t. No, I didn't. This isn't double angle. You just pulled the negative 16 out. Okay. And then you've got the Pythagorean theorem. Your k is then going to be negative 12 sine of t minus 0. So we end up then with negative 12 sine of t. All right, so This is going to end up being what? When we cross these two, let's not do that yet. When we cross these two, because then we're going to need to take the magnitude. All right, plus we're going to have 12 cosine t of j. That became a plus because we subtract the j term. And then we have minus 12 sine of t k. All right. The magnitude of this that's then going to be the square root. We're then going to have this negative 16 squared. Now, we're going to end up now, once again, with a cosine squared and a sine squared. All right, so this ends up then being 256 plus 144 cosine squared of t plus sine squared of t. All right. This goes to 1, just like it did before. So this is then going to be 20. Okay, so that's our top. Let's look then at the bottom, because the bottom of the curvature equation, the bottom of our curvature equation is we need to take this and cube it. So if we go back to our first derivative, this is then going to be 3 squared plus 4 cosine of t squared plus negative 4 sine of t squared. So we end up with 9 plus 16 cosine squared of t plus sine squared of t. All right, once again, that's going to go to 1. So this becomes the square root of 25, which equals 5. So my curvature for this particular problem is going to be 20 over 5 cubed. It's going to give me a 20 over 125, which equals then 4 over 25. At this point, I'd like to propose a 5-minute snack break. And when we come back, we will look then at our unit tangent vector and the principal unit normal vector, and how we can find curvature as well from those. The J component turned positive because when you do the cross product, you always make it so it's a minus minus, and that's why it became positive. It's one of the cross product rules, Chris. All right, are we ready to start? Okay. I saw the saddest sight on campus. I have to go to the second floor to use the restroom, but I saw the saddest sight. I'm going to take a picture of it. One of the doorways to one of the big computer labs, there's a plant growing outside because there aren't students here to trample the plant. Very sad. Okay, so we're going to start working with some other vectors, and these vectors also give us information of curvature, and this was something that Joe posted in the chat. So let's start off by talking about our tangent vector. All right, now it's really the unit tangent vector. If you know me, whenever I have a unit vector, I want to write it like this, but your author does this, and that's fine. All right, so, and you're going to just hear him refer to it as the tangent vector, but the way we find it is we're going to take the derivative of our position vector and divide it by the magnitude of the position vector. All right, so that's our unit tangent vector. And as I said, he's going to just, I think in the homework, I didn't write it down, but I think in your homework, he just says find the or he just says find, I don't know, I didn't write it down. Okay, the other one you're going to have to ask about, and I'll draw you a picture of this in a second, is the principal normal vector. All right, now the normal vector is always 90 degrees off from the tangent vector. It is an R prime on the bottom. I believe that's correct. Yes, that's correct. All right, the normal vector all right, that's going to be the derivative of the tangent vector over the magnitude of the tangent vector. Okay, now the binormal vector is the cross product between the two of them. Okay, so we call the binormal vector B, all right, and that's then going to be our tangent vector crossed with the normal vector. All right, so let me go ahead and draw you a picture of this, and then we will probably only get a chance to work one problem. Word of warning, don't wait till the last minute to do your homework on this. It will not go well. Okay, it took me a long time to do this homework. I've gotten the impression Skylar and Perla have both started the homework. Would you agree you need some time to do this homework? All right, so let's go ahead and see graphically what this looks like. I know it took me quite a while to do it, but maybe I was in a slow mood. You also just have to be very careful. All right, so we have some curve going on in here. All right, and the tangent vector, if we choose a point, and yeah, you're going to have a point you're going to work with, right? You can then get your tangent vector. All right, your normal vector is then going to shoot up like this. So this would be our tangent vector, right? It's tangent to a point on a curve, and this would be our normal vector. The binormal vector, and to be very honest, let me flip through your homework real quick. I don't think you guys ever actually were told to find a binormal vector. Is that true? I always taught binormal vectors in the past. No, you don't have to find it, okay? I don't think so either, but we'll go ahead for drill. Here is the binormal vector. Now, one of the things that Joe pointed out earlier, okay, is another way to find curvature, and you're going to use this quite a bit in your homework. All right, so another way for you to be able to find the curvature is then the magnitude of your tangent vector divided then by the derivative of your position vector. Okay. All right. So let's go ahead, and I'm going to go ahead and do a homework problem. I had another one prepped. Well, you guys tell me, would you prefer to work with sines and cosines or e raised to the t's? Let me know in the chat. The e to the t problems? Okay. And this one, actually, you have to do a trick on. So let's go ahead, and because it has that e to the t factoring. All right. Because, you know, this was the one, that doesn't help you. All right, the one I actually have prepped is a sine and cosine problem, but those just go away for us. So let's go ahead and do this as an example. I believe this is number 6 in your homework. All right. And that is, we want to be able to find our tangent vector, our normal vector, and then we're going to want to also find curvature. Right? And so those are the 3 things we're going to go after. And we are also then given this vector here. So we have 6 square root of 2, e to the 6t, and then e to the negative 6t. So this will give us another opportunity to be able to deal with that e to the t factoring business. Okay. All right, so first thing, let's go ahead and do, oh, you guys want to do some 142? I'm sorry about that. We want to draw some lines today and figure out the x and y intercepts. All right, so let's go ahead. In order to find t, they're actually kind of struggling with that. In order to find t, we're going to have to take the derivative of this over its magnitude, the derivative of that position vector. So let's go ahead and find the derivative of the position vector. All right, the 6 square root of 2, that's just going to be what? Oh, I'm sorry, I lost a t here, didn't I? There's a t here. I'm like, oh, that's going to be 0. How nice is that? And then we're going to be stuck. So please make sure you have the problem down correctly. You're going to have that t in there. All right, so this is then going to become 6 square root of 2, 6e to the 6t, and then we're going to have here negative 6e to the negative 6t. All right, so we found the derivative. That gives us the top part of our tangent vector. All right, now let's go ahead and look at the bottom part. All right, so what is this going to be? This is then going to be the square root of 6 square root of 2 squared plus 6e to the 6t squared, right, minus, and then here, oh, I'm sorry, plus a negative 6e to the negative 6t squared. Okay, things would have gone kind of south that way. All right, now I'm going to notice something. And one of the things I'm going to notice is I've got 3 sets of 6 squareds. So I'm going to pull that out. And let's see what we then have left. We have 2 plus e to the 12t plus e to the negative 12t. Okay, now we did something similar to this on a previous one, but if I take the square root of this one, I get e to the 6t, and if I take the square root of this one, we're going to get e to the negative 6t. All right, if we multiply them together, we'll get 1 twice, so that would end up giving us the 2. So that's where the 2 would come from. All right, so, no. I had a 6 squared, first term 6 squared, second term 6 squared, third term a negative 6 squared. So I just pulled a 6 squared radical. If you think about it this way, this would be a radical 6 squared, which would just be a 6. All right. So let's keep going. So this becomes 6. This is then going to be e to the 6t plus e to the negative 6t squared. Remember, the 2 gets sucked into it because the 2 is that middle term, because I've got a positive t and a negative t. All right. So this ends up then being 6 times e to the 6t plus e to the negative 6t. We have now found our vector, and then I'm going to have to show you a trick. So our tangent vector is then going to equal 6 square root of 2, 6 e to the 6t, negative 6 e to the negative 6t, all divided by 6 e to the 6t plus e to the negative 6t. All right. So I'm going to pull the 6 out up top, and I'm going to do some simplification. And this is where, oopsie, that's the wrong bracket. We go, and this is where, in my opinion, this problem gets a little tricky. I don't know if any of you have tried this problem yet, but this problem gets a little tricky at this point. All right, those 6's will cancel. That's pretty straightforward. All right, now we're going to have to take the derivative of this. Okay, in order to be able to get the normal vector, right, we're going to have to take its derivative. What I'm going to do, and as I said, this is kind of tricky. I want to make things a little easier for me when I take the derivative, because you're going to have to use a giant product rule. And so it still works out. I actually ended up doing it both ways. But the trick is to go ahead and multiply the top and the bottom by e to the 6t. The reason why is because it makes the derivative much easier. Why take the derivative? Because we need to find the normal vector, and the normal vector here is then going to be the derivative of the tangent vector divided by the magnitude of the tangent vector. So that's how we define the normal vector. Okay. No, we didn't take the derivative of the tangent vector, we took the derivative of the original vector. All right, so now, as I said, I did it both ways. All right. One way is you can end up with a tangent vector that looks like this: 1 over e to the 6t plus e to the negative 6t, square root of 2 e to the 6t negative e to the negative 6t. You certainly can do that using quotient rule. It is not fun, it's a little more painful. In fact, it was so painful, I ended up with the right answer that I went and looked at the solutions, and what the author did is he multiplied the top and the bottom by e to the 6t. When you do it that way, you then end up with a t vector. This is going to end up being 1 over e to the 12t plus 1. Now, I'm multiplying this by e to the 6t, so that's why this one goes to 1. We're then going to have here the square root of 2 e to the 6t. We're then going to have here e to the 12t. All right, and then this is then going to be a negative 1. Now, this just makes the derivative a little bit easier because it just reduces terms. Now, you might be asking yourself, how can you say those two are equivalent? If, for example, you put in t equals 0, what happens? This is going to become a 1/2 square root of 2. This is going to become a 1 and a negative 1. This is going to become a 1/2 square root of 2, 1, and negative 1. All right, so it doesn't matter which formulation, you end up with the same scenario if you put in a t equals 0 or a t equals 1. The second one is a little easier to take the derivative of, but after a lot of algebra, I got to the same answer. And the reason why is because we now have these ones involved. I wrote it like this because I think product rule is a little easier than quotient rule. Yes, we are now solving for the unit normal vector, but we had to get this first. Okay, we had to get the tangent vector. Now we will solve for the unit normal vector. So I guess I was looking ahead, so to speak. All right, we're going to have something like that. Okay, so I'm going to use product rule to take this derivative, right? So if we take it with product rule, all right, what you're going to do, and there's a theorem that allows you to do this, okay, you're going to basically do the first, and then you're going to do times the derivative of the second. So this is going to end up being 6 square root of 2 e to the 6t, comma, 12e to the 12t. And the only advantage of using this is you do get a zero term. If you don't do it this way, you still get a zero term. It comes out in the wash. It just comes out much later. All right, so that's the first term. Okay, and then we're going to have to deal with the second term, right? And we can, so that's then going to be a negative 12e to the 12t divided by e to the 12t plus 1 squared. And let me write it down, and then you can tell me if I need to show you how I did that. Oh, there's no square root of e there. Hang on. I'm getting ahead of myself. Hannah says yes. Yes, meaning that second term. Do I need to write that out in detail on how that works, Hannah? Okay. Would you like, does somebody need to see this one done up? That's fine. Does someone need to see this one done up? Okay. So let's go ahead and do that. And then we'll come back. We want to take the derivative with respect to t of 1 over e to the 12t plus 1. I'm going to rewrite this as e to the 12t plus 1 raised to the negative 1. So the negative 1 comes out front. This is e to the 12t plus 1 raised to the negative 2. And then we have to use chain rule and do the inside. So that's then going to end up being 12e to the 12t. So that's where that came from. So if we rewrite it back in fraction form, we're going to get a negative 12e to the 12t over e to the 12t plus 1 squared. Okay, now when we're adding together, right, and here, let me go ahead and start a new slide. And let me write down where we were. All right. So we ended up here. I don't know. Sure, why not? Let's put a problem like this on the exam. I think that's a great idea. All right. I don't know, honestly, I'd have to look. I don't think there's anything this complicated, but I would have to look. But that doesn't mean it's not a valuable problem. It's just long. It's not hard, it's just long. And you don't need to beat Skylar up. I just think students have a tendency to use that as a, oh, I don't have to now pay attention because it's not going to be on the exam. But it's on your homework and it's on your quiz. All right. Now, in order to add fractions together. Thank you for your opinion, Skylar. When it's time for you to teach the class, you can certainly do that. When we're looking for a common, when we have two fractions we're trying to add together, one of the things we need to do is get a common denominator, right? I can't add these two vectors together without a common denominator involved. So my common denominator on this is going to be e raised to the 12th t plus 1. So I'm going to have 1 over e to the 12th t plus 1 squared. The first thing we're going to have to go through and multiply it by, so we will end up then with, let's do it this way. We will then end up with e to the 12th t plus 1, right? We're then going to have what here? 6 square root of 2 e to the 6th t, 12 e to the 12th t, 0, minus 12 e to the 12th t, and then this is going to then be square root of 2 e to the 6th t, e to the negative 12th t minus 1. By the way, guys, since you're asking about the exam, you won't have the answer because you can't use any notes on the exam. In addition, you are required to show all your work. So if you figure out how to use another device and just plug this information in and out comes an answer, you get 0 points. All right, so when you, I'm going to skip a step multiplying it out so we can have time to actually get the normal vector. Okay, so this is then going to end up being 6 square root of 2 e to the 6th t, all right? And then we're going to end up having it, because this is a, because we have a negative and a positive, right? We end up in here of 1 minus e to the 12th t. All right. This just becomes 12 e to the 12th t. All right. And this is then going to be 12 e to the 12 t. And I'll let you guys work through the algebra on that. Okay, so what do we need to find now? Well, we need to find our t prime. Or we need to find, we found t prime, we now need to find the magnitude of this. So I think you'll see why this problem gets a little long. I'm going to write it this way. Just going to do that because it's all just going to come out. All right, and then we're going to end up in here with the square root of 72 e to the 12th t. This one, when we square this component here, right, it's going to end up being 1 minus 2 e to the 12th t plus 24 e to the, oh, it's not, that's just plus, no 24 there. All right, so we're going to end up with e to the 24t. And what's cool is then we're going to have plus 144 e to the 24t plus 144 e to the 24t. All right, I can pull a 72 e to the 12t out of these, all right? And when I do that, I end up with stuff canceling. This stays the same out here. All right, and then in here, now I'm going to pull the 72. I believe I can do that. Yeah, I can. So I can pull the 172 out of everything. So I'm gonna, or not 172, but 72. All right, and let's look at why I want to do that. I then have 1 minus 2 e to the 12t plus e to the 24t plus 2 e to the 24t. Why isn't that going to be 12? Oh, it should be 12. I made a mistake when I was writing this out. Let's fix it right here, folks. This shouldn't be 24, should it? 144, e to the 12, e to the 12. Oh, no, it should be 24. Oh, I pulled a 12t out. Okay. That's why you got to write all your work out. And yes, this is a 3-page problem. All right. And so this one's then also, this one was 24. This one was 12. And this one's 12. And yes, Hannah, it's all under the square root. Thank you for being with me. Okay, so we get stuff that cancels and we end up back here, right? Because I've got a whole bunch of 12t's under there. All right, and would you look what we end up with? And I'm not going to be able to take this one too much further, but I'll write the answer down for you. All right, 1 plus 2 e to the 12t plus e to the 24t. All right, and the reason why I wanted to make sure we got to this point, because then if you look at this, right, we're back to that problem we were talking about earlier, aren't we? This is then e to the 12t if I take the square root of that, isn't it? So I'm back to having a perfect square. All right. So this then equals 1 over e to the 12t plus 1 squared. Right? We're then going to have the square root of 72 e to the 12t, 1 plus e to the 12t quantity squared. All right? So yes, things cancel out for us. And we're going to end up then with 6 square root of 2 e to the 6t. That's from that 72 over e to the 12t plus 1. Now I did it another way where I did it using the quotient rule, and I got to the same place with the quotient rule. There was just a little bit more simplification involved. All right. So at this point, I'm going to go ahead, since we are running close to the end and you guys are getting tired, especially of this problem. We certainly can write out this, which is why we did all that work. All right. So that is then going to be 1 over e to the 12t plus 1 quantity squared. All right, and then we have 6 square root of 2 e to the 6t, 1 minus e to the 12t, 12 e to the 12t, 12 e to the 12t, all divided by 6 square root of 2, e to the 6t, divided by e to the 12t plus 1. All right, you notice you're going to get a lot of nice stuff to cancel. Your final answer on this for your n vector is then going to be 1 over e to the 12t plus 1. In here, you're then going to have 1 minus e to the 12t square root of 2 e to the 6t, and then you're going to have a square root of 2 e to the 6t. This is only 2/3 of one problem, and that's why you probably should start your 3.3 homework tonight and not wait until Sunday night to do it. Okay. So we are basically out of time. We will move into 3.4 next week. All right. I guess I can leave that up for you. So I'm going to have to go start the other class. I will post these for you, or if you'd like, I can send them to you. Why would we not have class on Wednesday? Yes, we have class on Wednesday. I'm completely confused. What's Wednesday, Eric? Oh, okay. No, we'll start 13.4 on Wednesday. Yeah, I can email you the last slide. All right, so I would strongly recommend you start your homework.